it's small. Looks like a big creek. It is a big creek. And they had awesome.
Okay, so good morning everyone. So today we're gonna start chapter 8. So we're done with chapter 6. So regarding chapter 6, there is the when we study the serviceability, we just covered the deflection part, okay? But the control of cracks, it's covered in the textbook and in the slides, but we didn't cover it in the lecture notes over, like in the lecture itself over here, okay? But if you would like to read it through it, just do so. If you have any question, please let me know, okay? So let me just adjust this.
Is that interesting? Who else is watching this? Who else is watching this?
Who else? No one is watching this except someone just in Little Rock at the beginning, just to make sure that everything is recording correctly. That's it.
Why are we doing it
To record it so that later on, if there is any need to use it.
Right.
Okay, so the control of cracks, we're not going to cover that, but we can go through it and read it in the textbook or through the slides that you have, okay? It's just two simple equations to just calculate the width of the crack, and then you compare that width of crack, okay, to a limited value, okay? So right now we're going to go ahead and start our discussion of chapter 8. Chapter 8 covers the shear and diagonal tension. So right now what we just studied is in all the previous chapters, okay? In chapter 2, 3, 4, 5, okay? We studied flexural in beam. So actually you have a bending moment, okay? So we said there can be three internal forces at a section. What are those three internal forces that can occur at a section?
Normal force, shear force,
and bending moment. So right now all we did is a design for that bending moment, okay? We still need to learn our design for a normal force and for the shear force, okay? So if there is a shear force, how to design the section, beam section, so that it's able to resist that magnitude of shear force applied in that section, okay? So right now, let's start with a simple example here. Let's say you have a simple beam. I always, when I explain, I give you this simple example, just simple beam, because that's the easiest thing. But in real life, okay, you're going to have a complicated structure. But at the end, this complicated structure will have the same internal forces at each section: shear force, normal force, and bending moment, okay? You have a uniform load like this, okay? So when you have a uniform load like this, let's say you draw the shear force diagram. How does the shear force diagram look like? You should be, able to do this, blindly, okay? You're about to graduate now, right? So you should know that this is the shear force diagram, okay, for a simple beam with a uniform load. The maximum shear occurs at the support over here. That's the maximum shear, okay? And let's say you want to draw the bending moment diagram. So the bending moment diagram would look like this, okay? It's symmetric, definitely, okay? So the maximum bending moment is right in the middle. The maximum shear is at the support, okay? So when you're going to design your beam for shear, you're going to base your design on the maximum shear value which occurs at the support. Even if you have a continuous structure, the maximum shear will be at the support. So let's say you have a continuous structure that looks like this, okay? Still with a uniform load applied on it. So the shear force diagram will look like this. So the maximum shear occurs at the support. Okay? Whether it's positive or negative, it's not going to make difference for us, the sign of the shear. Okay? The sign of the bending moment is so important, right? Because if you have positive moment, you're going to place your steel on the bottom of the beam. If you have negative moment, you're going to place your steel on the top of the beam. While for shear, it's not going to make difference. Okay? There will be no difference regarding, you know, is it a positive shear or a negative shear. Okay? So now, we have this shear force diagram, this bending moment diagram. Okay? If you have a bending moment M here, okay, would result in what? In stresses. What type of stresses would you have due to a normal bending moment? A bending moment gives you what type of stresses? Compression, tension. So it's normal stresses. Okay? It's normal stresses. And you know, simply if the stress-strain relationship is linear, the stresses would be, so this would lead, Fm would give you normal stresses, F which is equal to My over I. Okay, so it's normal stresses. If you have a shear force, V, what type of stresses would you have due to a shear force? Shear stresses, not normal stresses. How much is the shear stresses? Okay, you can call that tau. Okay, so if you have a shear force, you're going to have some shear stresses. Tau. How much is tau? V. Okay, V. Huh?
So your other one right hand.
Oh no, V. So tau. How much is tau? According to what you learned in mechanics of material. You have a shear force, you're going to have shear stress.
Something over JG, I think.
Little close, okay? So it's VQ over IB. JG is related to the torsional moment, okay? It's torsional moment. So VQ divided by IB. I is the moment of inertia. B is the width of the point where you're calculating your stress. Q is the moment of the area at the point, okay? So, for example, when you plot this at a section, it looks like this, okay? When you plot this relation here, you remember how did it look like? Like this, okay? Why? Because let's say this is your section. Q is the part that is changing over here. Here the width is constant. Any point here, as you go up and down, okay? B is constant. So B is not changing. V is the shear force, it's not changing. I is the moment of inertia of the section, it's not changing. What is changing here is that Q. Q is what? Let's say you want to calculate the stresses here, okay? The shear stress here. It's the moment of that area, okay? About that line. So it's this area multiplied by this distance. If you want to calculate the stress here, then it's the moment of this area about that line. Okay? So definitely if you want to calculate the stress here, what's the area on top of that line? 0. So that's why the shear here is 0. As you move down, the area increases. Okay? So the maximum is right here in the middle. If you go down, okay, you start, it's start gonna, when you take the moment, okay, you're actually taking it about, the neutral axis, so the distance to the neutral axis will start decreasing, if you take the moment here, it's that area multiplied by this, by the distance from its centroid to the neutral axis, which is 0. Okay? So that's why you have the stress here, 0, 0, and the maximum here. That's V max, or tau max. This is the stress, tau max, the maximum shear. Okay? So now, before we continue, I just want to let you know one important thing. Our problem with designing a concrete, element is not the shear force, The shear force, the concrete is able to resist the shear force, the direct shear force, The problem is, what's the problem that we have? What's the major problem with concrete? Weak in tension, That's the problem, weak in tension, And by the way, for the steel, it's the opposite. The problem is that steel, sections, they are so thin, normally they are so thin, so they are weak in compression, they would buckle. So again, for example, if you're designing a shear, or a section for shear in steel, you're not going to care about the shear a lot, but you're actually going to care about the compression that results from the shear. Here, we're not going to, our focus is not the shear force itself, but the tension that would result from this shear force. But shear force is a shear force. It will give you shear stress. Can it give you normal forces? Yes, that's what you learned in mechanics of material. Everything you learned was for a reason, So right now, this beam that we drew, it's a beam that has a section like this, At different points, there is a shear force and normal, or a shear stress and a normal stress, right? Depending on, so this is the normal stress that comes from the moment, and there is a shear stress that comes from the shear force, So let's take an element, let's say over here, small part of the beam. This small part of the beam, there will be normal stresses, F. There won't be normal stresses on the other face of that element, and there will be some shear, tau, on that face. It comes from the shear force, right? So now, if we just take that element, you understand now where does this normal stress come from? It comes from the moment. This shear stress comes from the shear force. If we just take this element here, so you have F, which is equal to my over I, and you have tau, which is VQ over I B, I want to find the maximum tensile stress at that point. What would you name, what name did you use to give to the maximum tensile stress? It's all in the mechanics of materials. Yeah, but it's a very, very, very important course, Everything is based on mechanics of material. So I wish I would teach that course,
We do too.
So, I told it before, but not in ASU, So, how you have a shear force, you have a normal force on this plane, Actually, the maximum stress would be oriented at some angle, And that's what you call the principal stresses, The principal stresses are the maximum normal forces that results from this, And it's going to be oriented by some angle theta, So here you're going to have some normal stress. That's the maximum normal stress, and the shear force is going to be 0 here. So that's the maximum normal stresses, okay, at some angle theta here. How much is that maximum normal stresses? The maximum normal stress is the principal stresses. So the principal stresses, you remember you used to call this, I don't know, I guess you used sigma, right? The notation sigma, sigma 1, 2, the principal stresses, okay, is equal to sigma x plus sigma y divided by 2 plus or minus square root sigma x minus sigma y divided by 2 squared plus tau xy squared. You remember this formula? Kind of, right? So that's the principal stresses, okay? One is the maximum stresses and one is the minimum stresses. One is positive and one is going to be negative, okay? In our case here, how much is sigma y? This is sigma x. F is the stresses in the x direction. Sigma y, how much is sigma y? 0. So sigma y is 0. And that sigma x, we're putting it as f. That's f. And we have tau here. So sigma 1 is f divided by 2 plus square root f divided by 2 squared plus tau squared. That's the maximum tensile force. Because concrete is weak in tension. So that's what I care about, the tensile force that results from the shear force. Okay? Let's see here. Let's take another element here. Over here, an element here. So let's say element 1. Okay? So add element 1. Yeah, sure. Here?
Yeah, I just need the box thing.
So now, at element 1 over here in this beam, it's right at the support, okay? So how much is the bending moment?
Minimum?
0, right? So the moment is 0. And how much is the shear force?
Max.
The shear force is maximum, okay? So for element 1 here, M is equal to 0, and V is equal to V max, the maximum shear force. Here you have V max over here, the maximum shear, and the moment here is 0, okay? So if we take that element, let's enlarge that element, okay, and study what type of stresses do we have here. So that's the element that we have here, okay? How much is the normal force? How much is this normal force? F? F is what? My over I, right? It's a function of the moment. So it's going to be 0. You don't have normal forces. How much is the shear, this shear force? Or shear stress, sorry? Tau? It's the maximum value. It's right in the middle, okay? Which is VQ over IB, okay? And this is going to be Q max, the maximum value of Q, right in the middle of the beam, okay? So that's the maximum shear stress. So if the moment is 0, so therefore F is equal to 0. If V is max, then tau is equal to tau max which is equal to that V max, the maximum shear, multiplied by Q max, the maximum Q divided by IB. Okay? Actually, this will give you 3 divided by 2 V max divided by the area. Okay? If you calculate Q max, okay, and I, the magnitude of I, the magnitude of B, you're going to have V max multiplied by 3 divided by 2A. Okay? So now, how much is, so the question is, I don't care about the shear stress. My problem is not the shear stress. Okay? What's my problem? My problem is the tension that results from this shear stress. Okay? So how much is the maximum tensile stress due to the given stresses?
Wouldn't it just be tau max?
Let's
If you do sigma 1, F is 0.
so yeah, so F12, the principal stresses, is sigma x, right? Sigma x plus sigma y divided by 2, those are zeros, right? Plus or minus square root sigma x minus sigma y divided by 2 squared, those are zeros as well, right? Plus F, or the tau, this maximum stresses, squared, right? So how much is F1 or F2? They are positive or negative, this tau max. Okay? You agree with this? So that means that on a certain direction like this, you're going to have F1, that's the maximum tensile force given in that direction. And here, the other principal stresses is the same magnitude, but it's negative, it's compression, F2. How much is that angle? So this angle, theta, okay, from the mechanics of material, you also learned how much is that angle, the angle for the principal stresses, tan 2 theta, okay, is equal to 2 multiplied by the shear divided by the stress, okay, or sigma x minus sigma y. So how much is sigma x minus sigma y?
0.
0. So actually, if this is 0, so you have tau divided by 0, tau max divided by 0, which is?
0.
No. Number divided by 0. 10 divided by 0 is what? 20 divided by 0 is what? No, not undefined. It's infinity. Okay? It's infinity. Okay? So tan 2 theta is infinity. Okay? What's the angle that its tan is infinity? 360. Okay. Just, you have your calculator, right? You have your calculator. Tan is what? Tan is sine 2 theta divided by cosine 2 theta. So you need to find an angle where the cosine is 0 and the sine is the number. What's the angle that cosine is 0? 90. So that means that 2 theta is 90. Okay? 2 theta is 90 degrees. So theta is how much? 45 degrees. Okay? So this stresses, this maximum tensile and compressive stresses happens at an angle of 45 degrees. Okay? So you have a shear force. So this is what we started with. We have a shear force in this direction. Actually, this shear force will result in a maximum tensile force in this direction. How much is the value of this maximum tensile force? It's the same as the shear stress. Okay? What's the angle here? It's 45. Okay? So actually now, my problem is not having a shear force. So in the beam here, in this beam, my problem is not having a shear force here. My problem is that there will be tension in this direction. Okay? There will be tension at an angle of 45 degrees. Okay? As the shear decreases, when you go in this direction, the shear decreases, this tensile force will still exist, but its value is going to decrease. Right? So my problem is that tensile force. Okay? So if you have a tensile force now, so let's copy the beam now, this beam. So over here, there is a tensile force in this direction, F1. The concrete is weak in resisting the tensile force. So what would happen to the concrete when you have a tensile force here? It will have, or it will develop a crack. So you're going to have some crack over here. Okay? At what angle? At 45 degrees. Okay? That's called web shear crack. Okay? Where would this web shear crack develop? It's going to develop here, right in the middle of the beam. Okay? Around the center of the beam. Okay? Where the shear stresses are maximum. Okay? When you move to the center, you're going to have cracks as well, okay? But maybe smaller ones. But as you move toward the middle, okay? Just a little bit toward the middle, okay? The normal stresses at the bottom of the beam will start to develop, right? Because of having bending moment, right? So you're going to have some bending moment over here. So it will develop flexural crack, and this flexural crack will join this web shear crack, okay? And it will develop just one big crack here. This one crack will not continue here because here the concrete is in compression, right? So you're going to develop this flexural shear crack, okay? It starts due to the flexural at the bottom of the beam and then due to the shear force, okay? So now you have this crack. There is a tensile force that is opening, trying to open this crack, okay? I have a shear force that is also applied on this shear crack, okay? I want to resist, okay? The problem is now my beam is cracked like this, okay? I'm afraid that it would fall down, okay? This part goes up, this part goes down, and then it breaks. Okay? Due to the applied shear force on that crack. So the beam breaks into two parts. So actually it goes like this. And then the other part here. There is a shear force here, okay? The shear force V. I just want to make sure that this surface has enough resistance to prevent the beam from, breaking on this surface here, okay? After developing this flexural shear crack, okay? So what is resisting, this shear force along that surface?
Just stay on the top, depression concrete.
Okay, so first here, you have some steel here that is under tension, okay? So there will be some dwelling force here. V, we're going to call this VD, okay? this concrete over here is in compression, it's not cracked, right? The top part, the green part here, okay? It's in compression, it's not cracked. Let me make this. So the concrete here will be able to give you some resistance, okay? V, we're going to name this V compression in the y direction. The compression, the concrete, okay, can give you some shear resistance here. The concrete in compression will give you some shear resistance here, okay? And then along this red surface, okay, this red surface is what we have here. This is actually, okay, if we just enlarge this part here, okay, it would look maybe something like this. It's not going to be a straight line. It's a crack, you know, that is, you know, corrugated a little bit, right? Why it would be corrugated like this? Because concrete is a non-homogeneous material. You have aggregates, right? So it's just going to pick around those aggregates, right? So actually, when you try now, those two surfaces try to slide along each other, okay? There is aggregate interlock. Those, you know, surfaces, there will be some aggregate interlock, okay? So that will give me some force, VA, aggregate V shear for the aggregate interlock. The vertical component of that is VAY, and the horizontal component is VAX, okay? So actually, let me draw this in the opposite direction. VA, so VAX and VAY, okay? So all of those forces are resisting the shear force, okay? The section is resisting the failure of this section through this force, VD, VAY, VCY, okay? So V, so the resistance given by the section is equal to VD, VAY, and VCY. Okay? How much is each term? That depends on the dimensions of the beam, how much is the shear force, how much is the bending moment, okay? But the ACI code makes things easy to you and says you can, the summation of those three terms, we're going to call them VC, the strength of the concrete. Okay? That's the summation of those three terms. That's the strength of that the concrete can develop on that surface. Okay? So how much is this VC? Okay? VC is given by the ACI code. VC is given by the ACI code in section 22.5.5. Okay? So it gives us two values for VC, or actually many values for VC. We have equation 22.5.51, okay, gives you a simple equation. For VC. That simple equation looks like this. VC is 2 lambda square root FC prime BD. Okay? And then there is another equation in table 22.5.51 gives you a less conservative value for VC, which looks like this, okay? It's harder to implement, but it will give you a larger value for VC. So you're getting a larger strength, okay? Row web, okay? V ultimate D divided by M ultimate multiplied by BD. Both, you can use any of those two equations, either this one or this one. Which one would you prefer to use? The first one, why?
It's easier.
It's easier, just, you know, FC prime and the dimensions of the section. Lambda, you know how much is lambda, depends on, you know, if you have a normal weight concrete, then it's 1. If you have lightweight concrete, then it's 0.75 or 0.25. In this equation, you still have FC prime, lambda, B, D, D, but you need to know how much is the shear force and how much is the moment at the section where you're finding the strength of that section. How much is the applied shear force, not the applied, the ultimate shear force and the ultimate hook bending moment. And rho, the percentage of steel that you have in your section. Okay?
If you're the one paying for it, you want to use that,
Huh?
right? So if you're the person paying for it, you want to use that, right?
Yeah, this one will give you a larger VC value, right? But it's harder to implement, but it's going to give you larger strength, okay? This one is going to give you less strength, but it's easier, okay? But practically, this one is, you know, the difference is not going to be that large, you know, okay? And at the end, you know, in terms of, you know, the savings, it's not going to be a lot of savings, but if you want to use this one to save a couple of dollars, that's fine. Okay? So now, this is VC, okay? There is another couple of equations, okay, that gives you VC. This is the magnitude of VC. Those equations here are the magnitude of VC if you only have a shear force and a bending moment, okay? What if you have normal force as well with them? If you have normal force with the shear force and the bending moment, okay, like in frames, okay, the equation for VC will be different. So the equation for VC, another equation here, this is equation, I guess this is in the table as well, table 22.5.51, okay, will give you VC equals to 2 lambda multiplied by 1 plus NU divided by 200 area gross multiplied by square root FC prime BD. This is if NU is compression. If you have a compression force with the bending moment and the shear force, okay, then VC is equal to that value. It depends on how much is the normal force. And it's equal to 2 lambda multiplied by 1 minus NU divided by 500 A, and this one is 2000 on top here, 2000, okay, AG. I don't memorize them, okay, they are in the ACI code. BD if and U is tension. Okay? So that's the shear force that the concrete can provide. Okay? The shear force that the concrete can provide. What if the shear force applied on that section, this shear force that wants to break the beam along that line, is larger than that VC? What will happen? It will break. What's your job now?
Make it a bigger chain stuff.
You need to make it, or make sure that it doesn't break, right? So you said, okay, increase the dimensions. No.
Just a bit more steel in it.
What we're going to do is we need to find some type of reinforcement for that line, okay, to prevent it from breaking, okay? and that's, you know, the shear reinforcement. Okay, so you need some shear reinforcement here. So what type of shear reinforcement will we provide? The stirrups. Okay, so when you have stirrups now, okay, stirrups goes like this. So it holds both parts together. Okay? So if the shear force, V here, is larger than VC, you need to provide some shear reinforcement to help the concrete. The concrete alone is not enough, so you need to resist this force by some stirrups. Okay? So if the concrete is not enough to resist the applied shear force, then shear reinforcement is required. How can you provide shear reinforcement? We can have three types of reinforcements. You can use whatever you want. The first type is vertical stirrups. The second one is inclined stirrups. Okay? Why would you have the stirrups inclined in that direction? Because that's the direction of the crack, right? So those are going to be more effective actually than the vertical ones. Okay? They are exactly perpendicular to the direction of the crack. Okay? So they would be more effective, but the problem is how you're going to put your stirrups inclined like this. That's difficult to sustain on site. So that's why people usually use vertical stirrups, not inclined stirrups. It's so hard to have this inclined stirrups. Okay? And then the third type is, what's that? We discussed this before, by the way, briefly. Bent up bars. You have steel here, and you're not going to need all of it on the bottom of the beam. So what you can do is you bend it up. This steel, as it bends up here, this bent up bars, it's going to be, very useful in, resisting the shear here. And it's oriented by some angle, maybe 60 or 45 degrees, whatever the bent up angle here that you have. So it's actually very effective in resisting the shear, having those bent up bars. Okay? So now, let's look on this example. How much stirrups do you need? You need to provide some shear stress, right? So actually here, to design for this the shear reinforcement, I have a shear force applied on the beam, V ultimate, at a given section. This should be resisted by the strength of the concrete, right? And the strength of the steel. Right? You agree with this? But the strength of the concrete and the strength of the steel, this is the nominal strength of them. Okay? So I have to multiply this by phi, the strength reduction factor. Right? I have to decrease the strength of the concrete by some reduction factor. How much is phi? It's always 0.75 for shear. What about that equation that we used to have? That's phi for bending, okay? Now phi for the shear is just 0.75. It doesn't change. It has nothing to do with the strain, the tensile strain, just 0.75, okay? So now, how much shear force should be provided by the steel? How much is Vs? It's V ultimate minus phi dc divided by phi. Just from this equation. So that's the shear force that should be provided by the steel. Okay? Okay, so now I know my steel should provide this amount of resistance, okay? Still, how many bars will I provide? What's the spacing of those bars? So let's see here. I have that section that we drew before. The beam looks like this. This part here. And then another part here. Okay? So I have my bars, my stirrups, joining the two parts, the two sections, two parts of the section. Okay? So this stirrup has an area ASV. Okay? Let me see here, AV. Okay? Now, if we say that the spacing between those bars is S, okay? I'm just going to assume here that this surface, just as an assumption, okay, to make things easy, this is 45 degrees, okay? And this distance here is D, so the width of the crack is how much? The vertical distance is D, this is 45 degrees, so how much is the horizontal distance of the crack? D as well. Right? It's 45 degrees, so it's 1 to 1. Okay? So the width of the crack here is D. Okay? The spacing between the bars is S, so how many bars do we have here in a distance D? If the spacing is S, how much is the number of bars crossing that crack? Number of bars crossing the crack. Yeah.
What is that AV?
What's what?
The AV, is that supposed to be the area still?
The area of the stirrups. The area of that bar. The area of the stirrup here. Its area across.
Okay, so it's supposed to be S or not?
It's area steel for shear. So it's the area of the stirrup. So we're just going to use AV. Okay? So how much is the number of the bars crossing the crack? It's D divided by S. Right? D divided by S by the spacing. Okay? So each bar can provide a force that is equal to AV multiplied by F yield, assuming that this bar is going to fail at yield, right? So each bar can provide AV F yield. But I don't only have one bar, I have N bars, which is D over S. So the stirrups will provide this amount of resistance, AV F yield D over S. D is the depth of the section, Fy is the yield stress of the steel that you're using, and that's limited to 60 KSI. It cannot be larger than 60 KSI. Even if you use grade 75, the ACI limit this to 60 KSI, okay? So what are the things that you can play with to increase your shear strength that is provided by the steel? It's AV and S. to provide more strength, you can increase the area of the stirrups, or you can decrease the spacing between the stirrups. You can have smaller S, or you can have more AV. So based on how much VS you need, you're just going to find a combination of AV and S, okay, to reach the VS that you need, okay? This is how you design the problem. You design for the shear force. First, you find the total shear. You have the total shear force. It should be resisted by the concrete and the steel. You find how much the concrete can provide from that equation that we said, 2 lambda square root FC prime BD, okay? And then you subtract this from the ultimate and divide by phi. You find how much resistance should be provided by the steel, and then you design for this steel reinforcement from this equation. So simple, right? Any question? Okay, we're going to continue from here next time.
We're going to get out early today, I forgot. Oh, you said we're going to get out early today.
Yeah, I tried.
They just taking attendance grade. Does that mean you're taking attendance grade? Some people are going to,
Yeah.
Oh, yeah. You aced that, didn't you? I promised 100 on it. I probably didn't do that good, you know? I got 83 or 4. Cindy didn't pass it really bad. I know. You're a passer. Oh, yeah, she didn't pass it. She really. She didn't make it funny for studying so hard for it. She keeps saying you don't study. I thought about it.
Okay. See you next week.
Interesting.